See my hair? Okay, let's get started. Okay, let's get started. Here we go. Here we go. We're going to start now. Stop talking. Ready to start. Okay, so let's do number 12 from the written. So it first asks for, you got this equation, right? And you got x's and y's, and this is different than a function because the x's and y's are like tangled up together. It would be very difficult, if not impossible, to write this as, to do some algebra so that we could write y equals something with all x's. Okay? So x and y is kind of tangled up in this equation, and we're used to what's on the right there. Y is a function of x, meaning that the rule is all involving x's and it spits out a y, a closed form. Okay, but this is a closed form where x and y are all tied together, and but in order to find, so this has a graph. It's all the points x, y ordered pairs such that those coordinates make this true. Okay, and that will be some curve. Okay, and we'll look at that in a second. So we can still think about at any given point on that curve, we can think about what is the rate of change of y with respect to x. And so in order to do that, even though this would be difficult to find like this, we just kind of pretend that it exists. Or in other words, the idea from this equation, the idea that y is a function of x is implied. Okay, it's not in your face, it's kind of hiding in the background. It's implied, or we pretend that we could write y as a function of x when we look at this. But we never do it. We never do it. We just pretend that it exists. Okay? All right, and that allows us, that idea of pretending that y is a function of x amidst this equation, then allows us to find the rate of change of y with respect to x for any point, for any ordered pair x and y. Okay, so part A says determine the x intercept. So no calculus yet, just how would we get the x intercept of this equation? Well, what's true about an x intercept? Okay, so along the x-axis, x could be anything, but so then it's a place where y is 0, or y is 0. So if we let y be 0, we're going to get sine of 0 minus 4x equals 2 to the 0. So this is looking for x-intercept. Okay, sine of 0 is 0 minus 4x, 2 to the 0 is 1, x equals negative 1/4. So we have, let's put it right there. At x equals negative 1/4, that's an x-intercept. So there it is. And then, but then there's a whole mess of other points that form a graph such that every x and y coordinate make that equation true, and that's the graph of this equation. Okay, so now we want to determine a general formula for dy dx. And you learned that through the video over the weekend, and you had lots of practice. And so let's just do one together here. So we're going to, this is called implicit differentiation. Implicit, again, it's because y equals a function of x is implied. It's hiding in the shadows, in the background. We never get to find that or do it, but we just pretend that it's there. Okay? So implicit differentiation means we're going to do the derivative one term at a time. So we look at this, sine of x squared y. Okay? And how do we approach that as a derivative, sine of x squared y. This is going to be chain rule. So we've got a interior function, x squared y, and we have the exterior function sine. And so I'll go inside out. Inside out would be then the rate of change of x squared y. And what's that? What kind of thing is that, x squared y? Product. Okay, so the interior function is going to be product rule. So we're going to do the first times the derivative of the second, which is y prime, or the rate of change of y with respect to x, plus the second times the derivative of the first. Okay, so that whole thing is f prime, the derivative of the interior, and then we're going to do the derivative of the exterior with respect to the interior. So derivative of sine is cosine with respect to x squared y. Okay, derivative of minus 4x. That's easy, minus 4. Derivative of 2 to the y. Okay, well, so y, remember y is a function of x. So this is chain rule. We have to think about this as chain rule because we're pretending that it's implied that y is a function of x. So we start with the rate of change of the interior function, which is y prime, times the rate of change of the exterior with respect to the interior. So that will be 2 to the y, ln of 2. Questions on, so we're applying all the same rules as before, but we're doing it term by term across both sides of the equation. And then anytime you're taking the rate of change of y, remember that y is a function of x. So the chain rule applies. And you're going to have this additional rate of change of y with respect to x. So that's the same as dy dx or f prime x. All those are fine, right? So this could be, you could write dy dx, you could write f prime of x, or you can write y prime. Those are all the rate of change of y with respect to x. Questions so far? Okay, so then what's the goal here? So the goal is to then isolate that dy dx, or that y prime, the rate of change, because we want to know what the rate of change of y is with respect to x. So we're going to multiply out all the terms, and then gather the ones that have a y prime on one side, and all the ones that don't on the other. Okay, so we're going to multiply out all the terms. Here we go. So we're going to have x squared, y prime, cosine x squared y. So that cosine x squared y is going to multiply in to both. It's going to distribute into both. Okay, then plus 2xy cosine x squared y minus 4 equals y prime times 2 to the y ln of 2. So now we've got 4 terms. 4 terms. So first of all, multiply everything out, get your 4 terms, and then everything that has one of these, I'm going to move it to the left side. Everything that doesn't, I'm going to move it to the right. So I'm going to have x squared, y prime. I'm going to keep this on the left. And I'm going to move this to the left. So it's going to be minus. Okay, stop. So if I lose you, stop me. But hopefully you had some success over the weekend here. This will be minus 2xy sine of x squared y plus 4. So I'm going to move these 2 terms that don't have a y prime. I'm going to move those over to the right. So everything with a y prime to the left. Everything without a y prime to the right. Are we good so far? And then the reason I do that, I'm trying to isolate y prime so I can factor it out. So factor it out. Y prime equals, or y prime times x squared cosine x squared y minus 2 to the y ln of 2.
Excuse me.
Yeah, please.
How do you get the positive 4 on the right side?
It was minus 4 here. So this is minus 4. You're going to add it to both sides.
Oh, okay.
And then equals minus 2xy cosine x squared y plus 4. I'm one step away now. All I need to do is divide by that thing in brackets. Divide by that thing in brackets. Let me get the final answer in red here so it stands out. So our dy dx, I'll write it, or y prime equals negative 2 xy cosine x squared y plus 4 all over, will it fit, x squared cosine x squared y minus 2 to the y barely fits. Usually it doesn't. Got lucky this time. Questions on finding the rate of change equation for this graph? Yeah?
So we used to take the derivative of d over dx.
What's that?
When we took the derivative, the rate of change for not the implicit derivative, was it d over dx equals? Because here we're taking with respect to y mass.
No, it's with respect to x. It'd be like d dx of y. Does that help? We're taking, this says take the derivative of that. And that's what we did. In this first step, right here,
It wasn't the same for the derivative. Was it also dy over dx?
yeah, it's always been dy dx.
How come?
What?
How come?
It's the notation for, it's one of the notations for derivative. So we have lots of notations for the derivative. F prime of x, y prime, dy dx. So d dx f of x, these are all notations for the derivative. They all mean the exact same thing.
So there is no such thing as d over dx?
That, no, just by itself,
Yeah.
no,
Okay.
that doesn't make any sense. It's saying take the derivative with respect to x, but you need to take the derivative of something.
Yeah.
So just d over dx doesn't make any, we never saw that. That would make sense. Okay, any question on finding the rate of change function? Okay, and why is it now that the rate of change function not only has x's in it, but also has y's in it? So why does it have x's and y's? How about right here with the green computer? Why does it have x's and y's instead of just x's?
Because in this situation, it's talking about with regard to the relationship between x with or y with regard to x.
Okay.
Y is relative to x.
Okay. Well, it was before when we had this. You know, we still had y with respect to x.
But then it was always like necessarily with y with respect to x. If you did it the other way around, it could be x with respect to y.
So I think that the answer to this question is if we graph this and take a look at the graph of this. So so let's graph this thing. Sine of x squared y. And sometimes with these equations you get some pretty cool graphs. Equals 2 to the y. Okay, so there's the graph of this. Zoom in one time here. Yeah, there we go. That's a good picture of it. Okay, so here's the graph of this, and there's our intercept, right? So let's see here. It looks like Does it ever wrap back around itself? I think if I remember right, there's more to this here. Let's see. Yeah. So if you explore a little bit, there's a lot more to it down here that you didn't know about, maybe. Anybody find this? So at first glance, you get this squiggly thing that heads up to the left, but then if you zoom right, there's a lot more to this graph of this, okay? And so here's the reason why we need y's and x's to get the rate of change, because what if I picked x was 0.1? There'd be lots of points with x equals 0.1, right? So you'd have this point, and then this point, and then this point. So just x equals 0.1 refers to many, many points. There's many, many ordered pairs x and y that make that graph true, right? So that they're on the graph. So if you want the rate of change of one of those, you'd also need to specify what y value you had, right? So that has a particular y. So now x and y together give you a unique point, distinct point in that graph, and then you would, if you plugged in that x and y together, you would get that rate of change. And likewise, down here you have the same x, 0.1, but a different y. And so those x and y together, plugged into this formula, would give you the rate of change there. Okay? So with these equations, you don't have y as a function of x. For certain x values, you could have lots of y's. But there's a rate of change at each one of those points. There is a rate of change. And so by having x's and y's in the formula, you can pinpoint exactly what ordered pair you want and get that rate of change for that ordered pair. Okay? So let's look at, what does it say? So we want to find the rate of change at the y-intercept. So what's the coordinates of our point at the y-intercept? Sorry, x-intercept, the one we found. So the coordinates there are, so let's reset the graph here. Right. Okay, so there it is right there. So I reset the graph. Looks pretty innocent here, right? Okay. So there's that point. So how are we going to find the rate of change right there, the rate of change? What is our point? It's going to be x value is 1 negative 1/4, y is 0. So we want to put negative 1/4 and 0 in here, and that's going to give us a number. And that number will be the rate of change of y with respect to x at this point, negative 140. Does anybody remember what it was? So save us a little time. Negative 6.3? Someone said someone else remember that? Negative 6.3? Okay, we'll take Adam's word for it. So if you took negative 1, 4, and 0, plugged it in here, it would crank out a number, and he's saying that number is about negative 6.3. And then the question asks, why does that number make sense? What does that number mean? Okay, yes, negative 6.3 is the rate of change of y with respect to x. It's the rate of change of y with respect to x. What does that mean? Tell the person next to you. We should have this by now. It's the rate of change of y with respect to x. What does that mean, negative 6.3? Okay, any volunteers? The rate of change is negative 6.3 of y with respect to x. What does that mean? What does that mean? Yeah?
Because at that exact point, that's the rate of change of a tangent line for
No, that's not what we've talked about. It's not. Sorry, that's not what we talked about. Yes, ma'am.
When x changes by a little, y changes negative 6.3 times.
Somebody's learned something. When x changes a little bit, at this point, y changes negative 6.3 times as much. Did you say that to your neighbor? Okay, by the end of the semester, hopefully we will all say that to our neighbor, okay? So let's prove it. I've zoomed in at that point, and we'll do a change of x of from here to here. I'm just going to see if it works, right? So my change of x is going to be so this is 2.498. So I think that's positive 0.0002. That might be too small. Well, I mean, if we had more decimal places, it would be fine, but we might not have enough decimal places for this. So I'm going to zoom out a little bit because we don't have enough precision in our numbers. But the more you zoom in, the more it'll be accurate, but only if you have enough decimal places. So let's zoom in just a little bit here. And let's do that. Okay, so point, do again. Make something nice. Oh my goodness. I'm zooming in, that's why it's so bad. Okay. Going the wrong way. Okay, here we go. So let's go 0.00 or 0.01. Is that right? Delta x equals 0.001. That's good. Okay, so I've got a delta x of 0.001. And when I do that, okay, that's about it. And so delta y is change in y. So now the delta x is up here, sorry. So this is our delta x of 0.001. Delta y
Is 0.001 times negative 6.3.
so I'm getting negative. We're checking that. So we're checking that calculation by looking at the graph. So negative 0.00633. Okay? And what did we say it was? 6.3? Yeah. Okay? So just looking at the graph, I'm just doing this by the graph. For a change of x of 0.001, the change in y is negative 0.006, which is a multiplier of k equals negative 6.3. And that confirms, so that's the number we would get if we took negative 1/4 and 0 and plugged it into our equation that we found in the lower right-hand corner for the rate of change. So if x changes a little bit, y changes negative 6.3 times as much as that. So increasing or decreasing, and is it increasing or decreasing, and is it increasing or decreasing slowly, moderately, or quickly? What would you say? So increasing or decreasing, slowly, moderately, or quickly? Decreasing quickly. Okay, decreasing quickly. And that's what that number tells us. At a rate of 6, it's decreasing 6 times as fast per change in x. Decreasing quickly, that's what that number tells us. If we zoom back out, we see right there, decreasing quickly at a rate of negative 6.3. Okay, the rate of change function gives us every rate of change for every point on the graph, not just this one. Okay, so that's the idea of the function. rate of change function. We'll give that particular number telling us what the rate is for any given point on the graph. Okay, any questions on that example? All right, so we're going to keep going here. Okay, so I have a ladder up against the wall, and then there's this monkey, and he's really tricky. He kicks that ladder out the bottom, and it slides down. Tricky monkey. All right, so we want to look at this context in terms of what we're talking about with all this rate of change stuff. Okay, so first of all, let's set the setup. A monkey kicks a 10-foot ladder. It's flat against the wall so that it falls as shown. How fast is y? Okay, so y we're going to call the distance from the top of the ladder to the floor changing with respect to x, and that's the distance of the bottom of the ladder to the wall. So let's see those. So, and then the ladder is 10. So let's pause it here. Be right there. So y is the distance from the top of the ladder down to the ground, and x is the distance from the wall out to the bottom of the ladder, and the length of the ladder is 10. Okay? So how can we, what are we asking for? It's saying how fast is y changing with respect to x? What are we looking for? Rate of change, dy dx, or y prime, okay, with respect to x. So we want, given a change in x, we want to know how much y changes for that change in x. That rate of change will change as the ladder falls. So it's a function. It's a function of the current value of x. Okay? So how can we represent the quantity being asked for? Okay, we just said that. That's dy dx, or y prime. Okay? And the question is, what do we need then to determine dy dx or y prime? So think back to your homework over the weekend. What is it that you had that you were able to find a dy dx or y prime? What do you need? They don't just, the dy dx doesn't just come out of nowhere, right? It comes from what? This is a key element in what we're going to do next. What's that?
Function.
A function. Is it a function necessarily? So, an equation, all right? So we need an equation of x. That's where all the problems you started with over the weekend were, you started with an equation of x and y, a relationship. And then you're going to find dy dx or y prime, okay? So now it's possible this won't be given. You have to come up with this. So this is kind of the idea of getting started in these problems. Instead of just, you're given an equation and you're going to find the derivative, you have to come up with that, okay? So, who wasn't paying attention? This is the one time all semester. Now we can, all right. So, what equation of x and y do we need, or do we have here? So we need an equation that's true, always true, no matter what the setup, what the configuration is. Is it always true? What's always true here? It's always equal to 10. What is always equal to 10? X and y is always equal to 10. What do you think about that?
Add it together.
Add it together. X plus y is always equal to 10. All right, what is always true? What relationship is always true? So think before you just jump to something. What do we have? What's our relationship between x and y and 10 that holds true? Yeah? Pythagorean theorem, okay? X squared plus y squared equals 10 squared. No matter where the ladder is, would you agree that that relationship always holds? Yeah. So that's going to be our equation. And so what are we going to do? We're going to find the rate of change of y with respect to x. Practice. You should all be able to do this. Go. See if you can do it. Find y prime, or dy dx. Go. I gave you the first step. This is an easy one, right? This should be an easy one. You should all be able to get it. He's just a monkey. He doesn't know any better. Okay, check your work. Should have gotten that by now. Okay, so if you couldn't do that or that was a struggle, then you got to get caught up, okay? That was a real easy one. Differentiating term, or taking the derivative term by term, you get negative x over y. Or, so you can say dy dx is negative x over y. Okay, how fast is the top of the ladder falling when it is 8 feet above the ground and when it's 3.5 feet above the ground? Go, see if you can solve this. How fast is the top of the ladder? Let me put it in the 8-foot position. There's 8 foot. So it's about 8 feet there. So right now, how fast is the top of the ladder falling per change in x? You need a slight bit of creativity here to solve this, okay? But you should be able to figure it out. What is 8 equal to? What is 8 in this situation? That's y. And what do we need to find dy dx? Just y? No, we need x2. How are you going to get that? What? Negative what over 8? How'd you get 6? Pythagorean theorem, right? So at this moment in time, when y equals 8, according to our original relationship, we can find what x is, right? X equals 100 squared equals x squared plus 8 squared, and x turns out to be 6. Okay, so when it's 8, the rate of change is negative 0.75. What did you get when it was 3.5? Negative what? 2.7. One more decimal place, how about? 6 what? 6.8. Someone else get that? Okay, so what do these numbers mean? So tell your neighbor, you got when y is 8, the rate of change is negative 0.75. When y is 3.5, the rate of change is negative 2.68. So what do these numbers mean? What story are they telling? What story are those numbers telling? Go.
Oh, I got it. I totally skipped that step.
Okay, somebody new. What does negative 0.75? What does that number mean? What does that number mean? How about back here? One of these guys. Walden. What does negative 0.75 mean? Okay. Negative 2.68 with respect to x. First of all, you changed. I was asking about when y is 8. When y is 8, this was our rate of change. Nicholas, what do you think? What does that number, negative 0.75, mean? Right, what does that mean? So just, it's the rate of change of y with respect to x. What does that mean? Say it nice and loud. Relative size of, not y to x. Matt. The relative size of x to y. No, tell me.
So it's or negative 0.75. The change in y is negative 0.75 times as much as the change in x at when y equals h and x equals 6.
For what kind of change in x?
Super.
Okay, really small. For a small change in x, y is going to change this many times as much. So the negative means what? Y is decreasing. It's getting less. Okay? It's getting less at a rate of 3/4 as fast as x is changing. X is going to change at that right around that time when y is 8 and x is 6. If x changes a little bit, y is going to go down 3/4 as much as x changed. You got to get this. That is the heart of calculus right there. That's why I keep asking it. Because it's rate of change is the heart of calculus. You got to know what rate of change means. Okay? So then what happens later? So a little bit later, y is 3.5. And now what's going on? Somebody new. Now what's happening? Somebody new. Tell me right here. Yeah. Right. For a small change in x, y changes negative 2.68 times as much as x. So what's the story then? So at 8 feet, the rate of change is negative 0.75. At 3.5 feet, the rate of change is negative 2.68. What story does this tell? What's that? Decreasing faster for the same change in x. As we get more, as x increases, we're getting a bigger and bigger change in y per change in x. So, and how do you see that? So the way the animation is going is x is increasing at a constant rate. Okay, so x is just increasing constantly. So look at how y changes. What do you see about y? At the beginning for change in x? Does y change a lot?
No.
No, in fact, it changes less than x, right? At the end, when x changes that same little bit, then y changes here almost 3 times as much. Oh. Okay, so please know how to interpret a rate of change value. So that's why I keep asking that question over and over again. Everyone in here should be able to interpret, and it comes down to this. Delta y equals k delta x. For a small change in x, the change in y is k times that change in x, whatever the k is, whatever the rate of change is. Okay. So here's what we did. So now we want to take a different kind of view of this. So this expression gives the rate of change of y with respect to x, how fast the top falls relative to the bottom moving. So the units of that would be like feet per feet. So per feet change in x, what change of y do you get? So that the unit would be like feet per feet. So now we want to ask, how fast is the top of the ladder falling in feet per second? All right, so that brings in a new quantity, okay? Time. All right, but we want to be really specific. What time are we talking about? The time in seconds. Always want to define quantities in these problems. Define them specifically when you start the problem. So just to say t is time, it's not specific enough. So write time in seconds since the monkey kicked the ladder, or time elapsed since the monkey kicked the ladder. That's a nice specific quantity you want to emulate when you define your quantities, okay? So now we have a third quantity, time. So if the bottom slides out at v feet per second, then the distance it's gone is v times t, right? Distance equals rate times time. So therefore the rate of change of x with respect to time is v. That's what I said at the beginning. It's a constant speed of v feet per second. So the symbolism for that would be dx dt. The rate of change of the distance x increasing with respect to time. And then we're calling that v. Okay, so we've got our equation that still holds true, but now if we want to know how fast the top of the ladder is moving with respect to time, what we're going to do is we're going to take the derivative not with respect to x like we've done every time, but with respect to t. So that means that x is a function of t, we're going to have chain rule there. And y is a function of t, we're going to have chain rule there. So every time we take a derivative, it's going to be chain rule because x is a function of t, here it is, and y is some function of t. So we have chain rule there and we have chain rule there. So what will the rate of change of 2x be? X squared. It'll be 2x, but then by the chain rule, we'll have the rate of change of x with respect to t. Just like we had so before we had to do that for y, but now we have to do that for everything because we're taking the rate of change with respect to t now, not with respect to x. So what's the rate of change of y squared? 2y times dy dt, or y prime, with respect to t. And then 100 with respect to t? 0. So now it's the same thing you did before, but when you take the derivative with respect to t, you have chain rule. This is chain rule with every term. Okay, you have it with every term, not just the y's. Not just the y's. Meaning you have to tack on dy dt, dx dt. Okay? So then same thing, now we're going to solve for, or just simplify it. So if I solve for dy dt, what's the meaning of dy dt? Well, that's how fast the distance y is changing with respect to time. So that is related to how fast the ladder is moving out, or that distance from the wall is increasing with respect to time.
The numerator of the equation dx, and we have dx inside the original equation. How's that? It looks like it would affect us.
I don't understand your question.
Yeah,
No, you're thinking something. But
I mean, like the X that has to stand for something. I just wondered why. It would be
X is the same X as before.
No.
So he's got the ladder like this. This is X, this is Y, and the ladder's length is 10. So this is the same. It's the same relationship of X and Y that we had before. Are you looking at this one or the next one?
I understand that one. It's the very last one. We have a negative X equal Y times dx dt.
Uh huh.
So dx.
This is think of this as a unit.
Okay.
That's dx dt is v.
Okay.
Just like it's a rate of change.
So with respect to time, how the change in y at k delta x plus one. It looks like the same.
No,
No? All right.
don't try to relate us to that.
Done?
This is the distance. This distance here, how it's changing with respect to time. It's a number. And then this is a rate of change of this distance with respect to time. So this is a k. This is a k. So it's not delta y equals k delta x. This is a type of k, and this is a type of k right there. Okay, so this is different than we've seen before. Why? Because we have two rates of change in the same equation. We've never seen this before. We've always had something, we found the rate of change. Well, now we've got an equation that has two different rates of change in it. The rate of change of the distance to the top of the ladder is related to the rate of change of the distance from the wall to the bottom of the ladder by this equation. So it's called a related rates equation because it's an equation that relates more than one rate. Could be 2, could be 3, could be 4. So then the question is, we talked about this earlier in class. What's the source of that? Where does it come from originally? This equation. Where did we get it? What's that? So how are we able to, what did we start with that we were able to find this? Yeah. Okay. The equation that related the associated quantities. Okay. So we had this equation of the quantities, x and y. From that, we could get the equation that related the rate of changes of those quantities. This is key. Because when you start problems, you have to have this mindset of, okay, I'm working towards a related rates equation. Where's that going to come from? It's going to come from the equation that relates the quantities. Okay, but semester after semester, students come into my office. They want help on these problems, and they can't tell me that. So I'm going to keep repeating it, but you got to get that. If you want a related rates equation, where does it come from? It comes from an equation that relates the associated quantities. In this case, x squared plus y squared equals 100. So if you're stuck, oh, these related rates equations, they're so hard. Okay? Did you know that? If you don't have that mindset, then you're going to never get off the ground. You're just going to be like, oh, I think I did this in physics, and I think you do this, and I think you do this equation, and then you do something like this. Okay, but this is the mindset you have to have. Okay, that if you want a related rates equation, you're going to start by getting the equation that relates the quantities. So that's what I'm going to ask you if you come to my office. You're struggling with these problems. I'm going to ask you if you have the big picture. The big picture is an equation that relates the quantities, and then you're going to use our implicit differentiation to get the related rates equation. Okay, did you hear me? Make sure it sticks. Here we go, one more time. To get the related rates equation, you first must have an equation that relates the quantities for those rates. Okay, so let's try some examples. Oh, but so did we never really answered this question. So suppose when y equals 8, how fast is it dropping in feet per second? So, of everything in this right here, what am I asking for? I'm asking for dy dt. Am I asking for x? Am I asking for y? Or am I asking for dx dt? Okay, I heard dx dt. Is that right? And when y equals 8, how fast is the ladder dropping? How fast is the top of the ladder, to say? How fast is the top of the ladder dropping in feet per second? Is that? Am I asking for dy dt, x, y, or dx dt? I heard dy dt. Yeah, dy dt is the y is that quantity distance at the top of the ladder. So dy dt would be the rate of change of that distance. The rate of change of that distance, which would also be how fast the top of the ladder is dropping. So in order to find dy dt, that means we need to know what x is, we need to know what y is, and we need to know what dx dt is. Do we have all that stuff? What is x when y is 8? We found that it was 6 before, right? So we would take -6 over 8, and then I didn't give you an actual value, but I said that it was v. So we'll just leave it as v. So if I gave you a v, 3 feet per second or something, for dx dt, then that would go there. So this is then dy dt at the moment when y equals 8. And if you had a number, v, if you had a number for that rate of change of x, then you would just put it right there, and then you'd get an actual feet per second for dy dt. Okay, here we go. The edges of a cube increase at a rate of 2 centimeters per second. How fast is the volume changing when the length of each edge is 50 centimeters? Okay, so here's how I suggest that you attack it. You got to think about this, that we're going to have a quantities equation, and that's going to give us a related rates equation. So then really what we want to ask is, okay, well, before we actually do that kind of main part of solving this, what rates are we going to relate? So what rates are we going to relate? So that's kind of the first question we're going to ask. So we're going to identify the specific rates involved. Okay? So what's one rate being mentioned here? And not a number, but in terms of the quantities. What rate? Okay, so you got 2 centimeters per second. That's a rate. The rate of change of what quantity with respect to what quantity? Yeah, so the length of the edge of the cube with respect to time going by. Okay? Any other rates mentioned in the setup here? Any other rates mentioned? It says, how fast is the volume changing? How fast is the volume? There's another rate. Okay? So there are two rates, are the rate of change of the side length with respect to time, and the rate of change of the volume with respect to time. So those are rates that are involved. Okay, so how fast edge length is changing, how fast the volume is changing. Okay, so now we want, so again, our whole thing here, this is up here to the right, this is our whole attack plan for this problem. Get a quantities equation and get the related rates equation. So we know our rates are how fast the edge length is changing and how fast the volume is changing. So now we need if we're going to do a quantities equation, what quantities are we talking about? And let's assign variables to those. So what quantities are we talking about? So how fast the edge length is changing. So what's our quantity associated with that? No, that's the rate. What quantity is associated with how fast the edge length is changing? Yeah. And what x means what though? X is what? Yeah. So if we want to know how fast edge length is changing, it's going to be edge length. Edge length is the quantity. All right. And then how fast the volume is changing. What's the quantity associated with that? volume of the cube. So she wanted x, I'm going to say s. Is that okay? All right, thank you. All right, so edge length we'll call s, volume v, and of course we have time here. Seconds, okay? So I really should say edge length of the cube. Volume of the cube would be specific, so there's no doubt. And then maybe time since cube started increasing. Or started growing, okay? Time since the cube started growing. So now we're ready to hit the main part of solving this. What do we need? We need a quantities equation that relates these quantities that we have. So we've got the edge length of the cube and the volume of the cube. And we need a quantities equation in order to get a related rates equation. Should be easy. Geometry, so we should know some basic geometry here. V equals s cubed. You should all be thinking that. V equals s cubed. So here, this step 3 here, this step 3 is our quantities equation. And you guys told me that was V equals s cubed. Or V as a function of s equals s cubed. And then the last, so now that we have the quantities equation, we want to get the equation that relates these rates. How fast the edge length is changing and how fast the volume is changing. And those are with respect to time. So what do? We use our differentiation that we just learned. And we're going to differentiate term by term with respect to time now. Not with respect to, before it was with respect to x, or in this case maybe s. Now we want to differentiate with respect to time. So that means we have, so this is function notation. So if we can just, this might be easier just to write the formula, v equals s cubed. So we want to differentiate v with respect to time. What is that? dv dt. And then we want to just differentiate this with respect to time. Nope, it's not ds dt. You need to differentiate, right? We're taking the derivative. What's the derivative? 3s squared, but then the chain rule gives us ds dt, okay? So we're going to have dv dt equals, confusing, look at that. Okay. Taking the derivative of v with respect to t, and then with s cubed with respect to t, which would be 3s squared ds dt. Okay, and so what are we trying to solve for? It says, how fast is the edge length changing? Which one of these? So now we've got a related rates equation. This is, now we just got to use it to answer the question. Which, it's asking how fast, how fast is the volume changing? So which one is the unknown that we're solving for? dv dt, s, or ds dt? If it says how fast is the volume changing? That's our unknown. So our unknown is dv dt. That means somehow we have to know what s is. Do we know what s is? It says how fast is the volume changing when the length of each edge is 50. So now we're at 50 squared. And then we need to know what ds dt is. 2 centimeters per second. That's how fast the edge length is changing. And so that formula right there is giving us how fast the volume is changing. So it equals 250, 500, is that 1500?
Yeah.
What's the units? It's dv dt, so it's how fast, how much the volume changes per change in time. So it should be per second. Okay, so again, in these problems, if you want a related rates equation, where does it come from? Did I do this wrong? 2,500 times 3. One more zero?
Yeah.
I'm not very good at math. Okay. All right, here we go. So again, what's the key? The key is this. Getting started, if you want a related rates equation, that will always come from the equation that relates the quantities. So you got to know what quantities you need, and you're going to know those quantities by starting by identifying the rates. So if you start by identifying the rates, then you've got the quantities for those rates, and then you can write the equation of the quantities. And then you're going to use our new technique of implicit differentiation with respect to t now, or whatever they're talking about, to get the related rates equation, right? This is a new thing for us. It's an equation that has more than one rate in it. So it's called related rates. Any questions on this example? Your turn. Okay, go.
That's okay.
Equation that relates the quantities involved. Equation that relates the quantities involved. So now you see the equation. So relates to the equation is that the rate of change in radius range.
Okay, are you thinking this? This is what you should be thinking as you get started. What do I need to get? What's my initial goal? To get what? A quantities equation. Equation that relates the key quantities. Trying to get that equation that relates the key quantities, because then I can get the equation that relates the rates involved. So you've got to have this mindset to make progress. I need that equation that's going to relate the quantities. Then I can get the related rates equation. Okay, questions? Keep going. So if you didn't have that mindset, you've got to change to that mindset.
It would just be like 1, derivative of b of 1. 1 times b. Not b times b.
This.
Yeah, what's the derivative of x? 1. So the same thing, derivative of b, b1, but then by the chain rule, times b.
Yeah. You're good.
No, because that's changing. 500 is it's not, the volume is not fixed at 500. 500 is changing, so there's a rate of change. You can't put, don't put the b in until you get to the related rates of change. Because b is changing. So its rate of change is not 0. Okay. The volume is increasing. Yeah. The radius is increasing. Good. That's right. You have to figure out what, so it's how fast it's moving. When the fluid has a volume of 500, so you have to figure out what the corresponding radius is where the volume is 500. Yes. 500 and 4. No, 150 inches cubed to the next. And this would be a short question, right? I thought you said that's what you're trying to solve for. Okay. Inches cubed. Inches cubed. Of what? Quantity. Inches cubed. What is that? The rate of change of volume per price. So let's use it. So
Yeah. I like it. Just derive that. So I'll do my next picture. This is right. So I have to derive that, right? Alright, so this just
Okay, let me talk through it. So the rates, see how you did, okay? The rates involved are this 150 inches cubed per minute, and then it's mentioning how fast the radius is increasing. Okay? So those are the rates. So what quantities are associated? Well, the first one, 150 inches cubed per minute, that's a rate of change of volume, because it's inches cubed per time. So the associated quantity is volume of helium in the balloon. Okay, I'm going to call that V. I'm going to call V the volume of helium in the balloon. And then we'll call R the radius of the balloon. Yeah, time is there, but we take the derivative with respect to time. So it's not going to be in our initial equation. Okay? So what equation brings together the volume of this balloon and the radius of this balloon? Not pi r squared. It's a volume. And we remember.
4/3 times pi times r.
Okay, there it is. We need to relate how the radius is changing with how the volume is changing, so we need an equation that relates the radius and the volume. And that's our V equals 4/3 pi r cubed. So now how are we going to get the related rates equation? So we've got the related quantities equation, now we need the related rates equation. So we're going to take derivative of V with respect to t. So if you want, you can do 1, right? So this is like differentiating x. Derivative is 1, if you want. 1 times, by the chain rule, dv dt. Or you can just say the rate of change of V with respect to t is just dv dt. Okay, now the rate of change on the right side with respect to t. So we'll hold on to the constant, and then we'll do 3r squared times, by the chain rule, dr dt. Why? Because r is a function of t. So yes, it's 3r squared, but r is a function of t. So by the chain rule, you need the interior, right? Derivative of the interior. What are they asking us to find? dr dt. So that means we have to be able to get r and dv dt. Do we have either of those? dv dt we have. That's our 150. That's how fast the volume is increasing. So we'll have 150 equals 4/3 pi times 3. Okay, so now how do we get r? It says the volume of the balloon is 500. We need to get the corresponding radius when the volume is 500. We get that, use this. So you plug in 500 for V, and you get the corresponding radius for a balloon of volume 500, which is, who found that? R equals? Nice and loud, quick.
4.92.
Thank you. Is that right?
Yes.
4.92 inches. So that's our radius when the volume is 500. So 3 times 4.92 squared. Now you're home free. You're going to solve for dr dt. And that will be the rate of how fast the radius is increasing per minute.
Quick question.
Yes, please.
We did the derivative of the 4 pi